be aware that there has been already a couple of talks on related topics by Rio and Wang. So just to make sure that we are all clear about what I'm going to explain to you, here is just a one-page summary of the result. Okay, so I'll be talking about symmetry protected topologically ordered ground states, and these states are known to be ideal resources for measurement-based quantum computation. The story more or less starts in 2012, where there's this ELSE paper, and they used group cohomological arguments to show that basically any 1D SPT chain is capable of performing quantum ware, essentially shuttling quantum information from one end to another. And you do this by a sequence of what are called symmetry respecting measurements. But this was only about where. This result was extensively expanded in 2017 by Robert and David and other people. And they extended this whole idea to basically all 1 qubit unitaries. And this was both technically and phenomenologically a large step, because the initial indications from the analysis from ELSE and others indicated that as soon as you try to perform anything apart from the identity gate, you invariably introduce logical decoherence in your system. And the way they got rid of it, I'll explain it more later, but the idea was basically a divide and conquer approach, where you split up the rotation angle you intend to perform into very small parts. You see these as d betas here, and then you separate them out by large distances in the middle. This makes sure that the rotations you are performing at these rotation sites are essentially independent of each other, and then at the end you can add them up, and the adding up is favorable in terms of the decoherence effect. Okay, so now having explained these two results, I'm in a kind of a proper place to explain our result now. So this new result I'm going to talk to you about says the following. It says, given a fixed number of qubits in a spin chain, so you are given a constant number of resources in a spin chain, and that is to your avail, the most resource efficient strategy is to pack the rotation sites as closely as possible, regardless of zeta. So zeta is kind of the typical length scale you would have in the problem in a SPT phase. It's the correlation length. And what this result says is that you to be most resource efficient, you should actually go to the exact opposite regime than what is prescribed in this 2017 paper. So you should actually pack your rotation sites as closely as possible. This will of course make the rotations you are performing dependent on each other, but nevertheless, this is the most resource efficient strategy to deal with decoherence in SPT phases. Okay, so at this point, of course, I haven't explained to you why this is true, but this is what I intend to convince you of in course of the talk through both analytics and numerical data. Okay, let me just stop for a minute and ask, are there any questions at this moment?
There's a question here.
Oh, yeah. In this most resource efficient regime, do you still have this scheme where you need to kind of turn the measurement record for every other site that's measured in symmetric basis?
Yes, you. So these things here are measured in the symmetry respecting basis just because MBQC. So these rotations here, they perform in the MBQC where they perform Z rotation. So these rotation angles will be kind of added up, not completely because now they are not independent of each other. But if you measure this on some other basis, this actually performs a X rotation. So that these, well, as you know, in the cluster case, I'm showing this for a state in the cluster phase. So these states here, these sites here, they correspond to X rotations, and these sites here correspond to Z rotations, and I'm just showing how to efficiently perform a Z rotation. So that's why the middle site is measured in the symmetry respecting basis. Does that answer the question?
Sure.
Okay. Any other questions? Okay, so this is the result. Let's just go back now to the very basics. I know everyone here is familiar with MBQC, but just for completeness, MBQC is a universal model for quantum computation, which is driven by projective measurements. So projective measurements plays the central role with the initial resource state, and then any computation is performed on this specific state by a bunch of local projective measurements. So it's really important that you keep the state the same and perform different measurements via different measurement patterns on the specific state. And if you can simulate a universal set of unitary gates via this procedure, then the initial state you started with is called a universal resource. And of course, the question is, this is just definition. Can you find actually these universal resource states? And yes, there are specific examples of them. They are called 2D cluster states, 2D AKLT states, and there are a bunch of them. Okay, so just for example, let's take the 2D cluster state here. I think you heard about the AKLT state from Wang 2 days ago. So in this talk, we'll focus more on the cluster state. The 2D cluster state is the canonical example of a resource in MBQC. You start out with, so the 2D cluster state is defined as a multipartite entangled state on a 2D lattice, and it's defined as the unique ground state of this local Hamiltonian with terms like this. So these Ka are called the stabilizers of the cluster state, and they are defined this way. So for each site in this lattice, you choose X for that site and Z for all the neighbors. So this was an example of a cluster state, and this is an example of how to perform computation on it. You basically measure the different qubits in different bases, and this essentially simulates quantum gates like C naughts, rotations about Z axis, and so on. Okay, so as I said, this was just a specific example. You can ask now the question, if I choose a state at random from a Hilbert space, how likely am I to actually get something useful? And the answer is it's extremely unlikely. Most states in the Hilbert space are actually too entangled to be useful at all for MBQC. Okay, so seems like we are not in good business if we just choose states and random, but let's not give up all hope. Let's add symmetry to the whole situation. So now we consider ground states of unique ground states of a family of local gapped Hamiltonians, and those Hamiltonians are invariant under some symmetry group, and we use those as a resource. And of course, because the ground states we're considering are unique, the states themselves are symmetric. Okay, and to a condensed matter physicist, this is the language of SPT phases. I think the idea of SPT phases was explained already 2 days ago, but just to remind everyone, two states are said to be in different SPT phases if their parent Hamiltonians, which I call H0 and H1 here, cannot be connected through a symmetric path without closing the spectral gap, but can be connected through a symmetry non-respecting path without closing the gap. Okay, and this whole idea about using SPT phases as MBQC, sorry, I think my computer went off or something. Can you hear me still?
Yep, we can hear you.
Okay, so this whole idea about SPT phases being used for MBQC comes from, I think, a 2009 paper by Akimasa Miyake, where they use some hybrid version of MBQC. But at any rate, all these ideas give rise to this conjecture that MBQC resource power is uniform throughout a SPT phase. And now at this point, this is just a conjecture, but next we'll see some actual theorems that give credence to this conjecture. Okay, so this was the result I was alluding to in my introduction. So this is symmetry protected where this was a seminal result in the topic by Else and others from Sydney. They essentially showed that computational ware persists throughout 1D SPT phases, and you can perform quantum ware, namely you can take the information encoded here to here without any logical decoherence at all. And this was done through the machinery of matrix product states and group cohomology. So the topic of group cohomology is already well studied in the context of SPT phases in condensed matter physics. And this paper was really important in the sense that it brought all those machineries into quantum information and actually used those methods to actually compute things in the SPT phase. But this was, as I said, only for quantum ware, no actual rotations about any axis. And worse, the same analysis seemed to suggest that if you actually try to perform anything away from the identity gate, then you invariably introduce logical decoherence in the system. So that seems to be a dead end. But in 2017, this whole issue was circumvented by Robert and David and company from our group. So the idea here was that the logical decoherence, it exists, but it can actually be efficiently managed via this scheme that they called oblivious ware. So this can essentially be done because in this oblivious ware construction, the decoherence that occurs is essentially a higher order effect. So to fast order, we see that it's effectively completely a unitary circuit, unitary evolution, and the decoherence effects come in larger orders. And because it's a higher order effect, you can employ a so-called divide and conquer strategy. So you can actually take the rotation angle that you want to actually perform on your logical qubit and divide it into small parts, and then separate these rotation sites out as far as you want. So, and just making sure that they are completely independent of each other. What this does is it allows you to reduce the decoherence, and this is because, as I said, it's a higher order effect. So at each site, you are performing a rotation of beta over m, where m is the number of splittings. So d beta is beta over m. So the decoherence at that site is proportional to beta over m squared. And because each of the rotations are independent of each other, at the end, you can just add up the total decoherence. So you get beta squared over m in total. And of course, now as you increase beta, this decoherence decreases constantly. And in a SPT phase, you can increase m as much as you want, and you can basically get rid of all the decoherence. Okay, so this was about 2017. Are there any questions about this? Doesn't seem to be the case. So at this point,
Yeah, I actually have a question. So is there
yeah, go
some
on.
intuitive explanation why it's a second order effect and not first order?
I don't know if there's a intuitive explanation. It's basically this addition of incoherent addition of measurement paths, and if you do the calculation of, I mean, this essentially simulates a quantum channel, and if you do the calculation, I think it turns out that it's up to fast order, you get essentially a unitary, and then the higher orders deviate from the unitary.
Thanks.
But maybe Robert is the better person to answer this question.
Yeah, okay, if I may just inject. So consider the following super operator. You have probability of 1 minus p, dominant, let's say p something small, 1 minus p rotation about the z-axis in a particular angle, and plus p super operator rotation about the opposite angle. Yeah, and you work that out for small angles alpha. This is nearly a unitary. I mean, you can just work it out, and then the deviation from unitary to the right is second order. This is the calculation to do. Why this is the calculation to do is a long story.
Thank you.
Okay, are there other questions? Okay, doesn't seem to be the case. Okay, so this was the story of 2017, but so now at this point, you should ask yourself, like, what else can you ever want in a 1D system, right? Because we have basically gotten rid of all the decoherence and we can perform any arbitrary rotation that we want. But let me just remind you that all the analysis I talked about right now from 2012 and 2017, all of these techniques only work in the infinite, basically the thermodynamic limit, where the concept of a phase is valid. And in the thermodynamic limit, of course, no one is interested in resource efficiency because you have infinite resources. In a thermodynamic limit, you have infinite number of qubits, and nobody stops and asks the question about, can we investigate other regimes where things can be more efficient, because efficiency is not a concern. So all these tools about group cohomology and things like matrix product tensors decomposing into logical parts and chunk parts, things like this, all of this work in a setting of thermodynamic limit where no one cares about efficiency. But now, last year, mainly due to Robert, there was a new formalism developed in the group. This work hasn't been published yet, but hopefully it will be published this summer. This new formalism focuses solely on the symmetry group at hand and the spatial pattern by which the symmetry acts on the chain. And this new formalism actually allows buys us a lot of things. Namely, it applies to systems of arbitrary size. So we can actually deal with systems of, let's say, 50 qubits or like 10 qubits. I don't know, like arbitrary size qubits. And of course, in those size qubits, it is important that you make the most of your resources because resources are limited. And this is, of course, specifically significant in NISQ devices where we are trying to get the most out of these noisy devices. Secondly, this formalism allows us to investigate new regimes of MBQC, like the regimes where these operations are indeed dependent on each other. And these two parts will be the most important, relevant for this talk. But I think Wang gave you a glimpse of the third part, that this formalism also makes a direct connection between computational order parameter and string order parameters. But we won't deal with that terribly much in this talk. Okay, so what is this new formalism? Of course, I'm not going to give you the full formal version that Robert came up with, partly because I still don't understand parts of it. But this is the essential idea. So the basic idea is to simulate MBQC experiments operationally. Namely, you just perform a MBQC circuit like this. So this is a standard MBQC circuit that typically is performed on the cluster state. So what you do is you measure a bunch of these, most of these qubits are measured in the symmetry respecting basis, and one qubit here is measured away from the symmetry respecting basis. And the final qubit here is used for readout purposes. So it's measured in all kind of bases. like all Pauli bases is X, Y, and Z, let's say. And the circuit version of this whole diagram is you prepare a plus eigenstate. So, so this is the +1 eigenstate of the Pauli X operator, and then perform a rotation on it, and then measure the last qubit in X, Y, or Z base. I mean, at the end, you measure it in the X, Y, or Z basis. And just by using some MBQC relations, so these relations basically relate the output, 1-bit output, with all the outcomes of these different measurement outcomes and the symmetry in the cluster phase. So the cluster phase inherits some kind of symmetry, global symmetry. And if you just use that, then you find that the expectation values of the qubit, the logical qubit, look like this. So let me just explain. Of course, I'm not saying where they come from. These are results from a calculation, but this is what they look like. So they look like cos beta for the expectation. Is there a question? No. Okay. So the expectation value of the logical X operator is just cos beta. So it's independent of where you are in the cluster phase. So this kind of makes sense if you think of beta, at least when you take beta equals to 0, that corresponds to a quantum where you see that you recover the plus state. So you started with the plus state and get the plus state back. The expectation value of Z is 0 just because you start with a plus state and then you're performing a rotation about Z. So you started at the equator and you're still staying at the equatorial plane. And the expectation value of Y is sine beta, but it's modulated by this expectation value here. So what is this expectation value of an operator? And this operator, it just comes out from the calculation, is this thing here. And people working on SPT phases might recognize this as kind of the standard string order parameter in the SPT phase. So you see there are these boundary charge operators here and the symmetry being repeated in the middle. And this is the standard string order parameter that I think there was mention of this by Austin, I think, on Monday. But this is what shows up in this calculations. So you can see that this plays the role of a computational string order, computational order parameter here, because if this is 0, there is basically no rotation, and if this is 1, this is actually a perfect rotation. Okay, so that's kind of the simplest example of what results you can get out of this formalism. And okay, so now, yeah.
Yeah, oh, so could you explain a little bit more? What is this X bar, Y bar, Z bar? Is this like the average of X, Y, and Z that you get from this tomographic measurement that you do at the end? Or
Yes, exactly. So it's the expectation value of the logic. So if you think about the logical space here, it's the expectation value of X. If you measure a bunch of X here, it's the expectation value of Y. If you measure the last qubit in the Y basis, it's the expectation value of Z. If you measure this in the Z basis.
in the physical space, does this exactly correspond to just the local single site X, Y, and Z operator on that last qubit? Or is it like, I don't know, X, Y, and Z with some sort of long string of
I can't hear you extremely well. Can you repeat your question again?
Well, on the physical space, what is this?
Turn around, speak to the owl.
Oh, to the owl. Okay, yeah. On the physical space, does this what does this X bar, Y bar, and Z bar correspond to? I guess not in the.
But they are not physical operators. They are logical operators. These things are physical operators here. The bars always represent logical operators.
Okay.
So may I ask a question?
Yeah, sure.
is this relation is in the whole cluster phase or just for the cluster state?
Say that again. Sorry, I couldn't hear the last part.
Is this relation is for the whole cluster phase or just the cluster state?
This relation is for the entire phase.
So the boundary operator do not change in the whole cluster phase, like the ZX?
No, they are the same. This is the operator. It's just the value of this expectation value changes as you go along in the phase. So this value will change depending on where you are in the phase.
Okay, thank you.
You're very welcome. Okay, so let's now do the next kind of logical thing. Let's try to see if this new formalism gives us something new for this divide and conquer mechanism that we talked about earlier. Let's just now take this rotation angle and split it into two parts. I just call them gamma, but gamma is basically beta over 2. So I have now making two rotations at these two sites. I'm calling them site K and site L. And the distance between them is delta. Now, for clarification, now delta, I'm not assuming anything about delta. So delta is just a free parameter. I can choose delta to be large. I can choose delta to be small. It's just a free parameter in the problem right now. And I'm making no assumptions about anything else. Okay, so just using the same techniques that I kind of alluded to in the previous slide, you find the expectation values of, well, this should be bars. Okay, yeah, just to be consistent, I'll make them bars. They look like this. So, okay, let me explain what is going on. So there's this gamma. Gamma is the angle by which you rotate. And then there is a bunch of these operators here. This is K, comma L, and then there's this K plus, KL plus. So what are these? So this is again a string order parameter, but this label at the bottom basically tells you where the string order parameter starts and where it ends. So this is a string order parameter that starts at the site K and ends at site L. So these are the boundary charges. And these ones, they start at site K, and the plus just represents that this ends at the, so this starts here and ends at the last qubit, and this one starts here and ends here. And this is exact. So this is true for any point in the SPT phase, and this is valid for any values of delta. Okay. And then because you are in a short range entangled phase, what you can do is you can argue that this is basically, and you are in the bulk, this is essentially just a function of this distance delta string, because it's a string order parameter. And you can write it as this. This is just a kind of a redefinition of this, where I've redefined it as F delta. The F delta thing just captures the way this decays. So this K delta, this decays as a function of delta. The F delta just captures this decay. This is just some redefinition of K delta. It's just useful for my calculations later, but there is nothing fundamentally going on there. Okay, so there was a question in the chat. You said gamma is beta over 2. Did you mean beta squared over 2? No, gamma is beta over 2. So I'm splitting the rotation angle into 2. So if delta is large, these rotations angles can be added up. So if it's beta over 2 here, beta over 2 here, then the total rotation angle is just beta. So you just divide them by a factor of 2. It's not beta squared over 2. Okay, and then so just to do some consistency check, you can define any loss in purity measure, like how far is the density matrix, from the surface of the block sphere, and then you can verify for yourself using these relations that you do recover this 1/2 factor for if delta is very large than the typical correlation length compared to delta equals to 0. So delta equals to 0 means there hasn't been any splitting, and then delta greater than this correlation length is basically when these two sides are independent. But more importantly, we can actually do more. So this is just a consistency check, but I am not required to choose delta greater than zeta, right? I can choose delta to be any value I want, and this is just better explained by this numerics. Okay, so what do these plots show? Okay, so this is just some normalized version of the loss in purity, and this is I'm varying delta, and these 4 plots are essentially for 4 different points in the phase. So this point here is very close to the cluster state, and these points here are essentially very close to the phase transition. And you can see that the correlation length that is kind of characterized by this curve is increasing as you go from this to this. But as I said, you can choose delta to be any value you want, and you can explicitly see what the loss in purity was for those points. So you see, they all start at 1, and all of them just settle at the value half, but each of them take different values of delta to actually settle there, just because the correlation length is different for different points here, here, and here. But as I said, now I can actually get these values and actually fit a curve here and see the general trend at delta equals to, let's say, 4. What is the loss in purity? And this will actually help us to go to these regimes where we can see the explicit like loss in purity for different values of delta, and see other regimes where the rotations do become dependent on each other. Okay, are there questions about this plot? Doesn't seem to be the case. So let's go. Okay. Okay. So let's. Is there a question?
Oh, I need to speak to the owl. Did you explain the values in this plot? I mean, you explained the correlation, but why do they level out at 1/2? Did you say that?
I think I explained that here. So
Oh yeah.
the loss in purity when, okay. I think let me explain it again. So when delta is very large, these two rotations are basically independent of each other, and then you can use the argument that I already explained to you in the 2017 paper, that you were basically, what you are basically doing is, so the total decoherence goes like gamma squared at each site, and then there are 2 sites, so it's 2, but gamma is beta over 2, so beta over 2 squared times 2, and this gives you beta over 2, and there you see there's a factor of 2 that comes, and that's the factor of 2 you see in these plots. So each of them just settle to half each of the time. Okay. Okay, now let's do the arbitrary number of splittings. So we consider that you have a fixed number of qubits now. So n is the total number of qubits that you use as your resource. And let's imagine that you do m splittings, and each of the consecutive, like the 2 consecutive sites where you perform the rotations are separated by delta. So of course, now there is a constant. You cannot just increase m arbitrarily without decreasing delta, because m times delta is fixed. Okay, so now there is of course a trade-off, because if I want to make the rotations independent, I need to make delta large, but delta will make m smaller, And increasing m and increasing delta, both of them actually decrease, makes the decoherence less. So which one should I increase and which one should I decrease? That's the question. You can, I'm not going to show the calculation because it's not terribly nice to see, but if you do the same things I talked about and use a perturbative expansion in beta, then you get an expression like this. So you get something proportional to beta squared, which is good because we know that the leading term in the decoherence should be proportional to beta squared. Then there is a term which is independent of delta, so let's not care about it too much. And then there is a function that I name f delta, not a very imaginative name, but I'm not right. It's written here, but it doesn't look so nice and it's not terribly important. The important thing is that this function is a strictly increasing function of delta. So this function here is increases strictly as you increase delta, and so thus the loss in purity also increases monotonically as you increase delta. Yeah, I don't want to explain this mess, but let me go to the next slide. Maybe the picture will tell a better story. Okay, so what is this curve? Let's see. Okay, so on the y-axis, we have the loss in purity. It's normalized by the loss in purity when you did nothing. So you just performed a single rotation. And on the x-axis, you see the distance between rotations, so the delta here. And I'm doing this for, so this is kind of, this is not very clear, but this, what this means that I'm performing all these calculations in at a point where I'm very close to the phase transition. So 50% is the phase transition point. I'm doing this at 48%. So I'm very close to the phase transition between the cluster phase and the product phase. And I'm also doing this for a fixed number of total qubits at hand, that is 120. Okay, so this is what I'm doing. And this curve here, the dotted green line you see here, this is the curve is delta over n. And if you just remember the definitions, then delta over n is just basically 1 over m, because n is m times delta. So this is this 1 over m curve that goes through the origin here. And any deviations that you see from this curve basically tells you that the rotation angle, the rotation operations are becoming dependent on each other. So you remember when delta was larger than the correlation length, you should always see this 1 over m dependence, and any deviations you see is telling you that now the rotations, you cannot treat the rotations independently. So you see up until this point, they seem to be completely following the curve, but after this, they seem to deviate. And you see they go up, meaning the loss in purity is not, so this thing is going up, meaning the reduction procedure is not working as efficiently. So the loss in purity is kind of more than what it would have been if it had stayed in this line. How, and this is understandable because now the rotations are becoming dependent on each other. So of course they are going to introduce more logical decoherence than if they were independent. But the most important point is that even with this thing going this way, this doesn't ever go up. So the minimum loss in purity occurs at this point where delta is the smallest. So if you want to reduce the loss in purity, the maximum, then you actually have to choose this point here. And this point actually has the largest deviation from this line, meaning that the rotations are mostly dependent on each other at this point. Are there any questions about this slide?
Yes, Arnab, can I ask a question? Can you hear
Yeah,
me?
sure. Yeah, I can hear you.
So you showed these results for 120, but how does it scale with this plot?
Oh, 120, it doesn't matter. I mean, I just choose 120 because it's a composite number and I can get a lot of things. I think I also did this for
But let's say
200 and, yeah, go on.
But let's say you do 60, 80,
Yeah,
100. So you get the curves on top of each other. This and also I don't understand this 48% into sweep. What does it mean? Sorry.
No, it's okay. That's bad notation. So this just means that you are, so 50% just, so if you, so the sweep is basically interpolating between the cluster state and the product state, and 48% into the sweep means like you are very close to the phase transition. So the phase transition happens at 50%. You are almost at the phase transition. So the correlation length is large. Does that kind of?
Yes, but the in a finite system you don't have a phase transition yet, right? So we have discussed this in the past, right? So
yeah, that's correct. That's correct. But you can still define a correlation length. I mean, in this plot, you see that if you go to 48, there is this, of course, you see this correlation length is larger than what you would expect if you're closer, right? And that's all I care about is, I mean, the reason I want a large correlation length is to see a more pronounced effect. Of course, if the correlation length is very small, you will not see visible effects, because even if you pack the rotations very close, because the correlation length is so small, they are still independent. So you will not see any effect, but I'm just choosing that point so that I can demonstrate the effect better.
Okay, maybe I can rephrase my question. So let's say you do a number of qubits half of this 120. You will deviate from the green curve sooner or later as a function of delta?
Let's see. I don't know from the top of my head. The answer should be somewhere. Okay, I don't think I can answer that question immediately. I have to think a little about it. Of course, I can do numerics on it and just see it, but I don't have an answer from the top of my head.
Sure. Just curiosity. Thanks.
Yeah, not a problem. Other questions? Okay. That kind of brings me to the end of the talk. So here is the take-home message. It's basically a copy of what I said earlier. So to make the most of our resources, we should pack the rotation size as closely as possible. And it doesn't matter where we are in the phase. So we should always choose delta, the smallest. And in this regime, the individual rotations become dependent on each other. And thereby it introduces more logical decoherence. However, the penalty that is paid in this regard is more than compensated by the increase in the number of splittings. So because you can increase M more, and that kind of wins in the long run. Okay, that's basically everything. So in this talk, I focus mostly on the cluster phase, but the same techniques and the results actually stand for any SPT phase where you can define a correlation length and fit a exponential in the string order parameters. But it's a kind of open question as to if these techniques can be applied to gapless phases where these string order parameters decay polynomially. Okay, thank you for your attention. And I think that's all I had. Maybe I should take questions now.
I have a question. Can you hear me, Arnab?
Yeah. Is that David?
Yeah, this is David.
Yeah.
Thanks for the nice talk. I was wondering, so you showed these plots where the purity is maximized when the things are close together, right? When the measurements are as close as possible. But do you know when they're really close, like like the purity is high, but do you know that you're actually doing the rotation that you want to be doing?
Yeah,
Okay.
I am taking that into account. Yeah, I'm doing the rotation. I'm fixing the rotation at each step. Yeah.
But like, but like, you know, like the net effect of all of these closely packed rotations, the fact that they become kind of correlated, like
Oh.
you said, that doesn't affect the overall logical rotation you have at the end?
I think that's because it's a higher order effect. I think you can still add up the rotation angles because in the first order, it's still the same. You can do the analysis and see. Yeah.
I see. Okay. Okay. So
I think the dependence only comes in the decoherence. Yeah.
I see. Okay. Thanks.
So I wanted to ask a question about the critical exponent of
Yeah.
your normalized loss impurity. So did you try to figure out what is the critical behavior across the phase transition of this like correlation length or some other parameter?
Yeah, I think I tried to do that. So I think the critical exponent was like 2/3, if I remember correctly, which is kind of weird because I think there is a one-to-one like Jordan-Wigner transformation between this one and the Ising model, and then the Ising model correlation length of course has a critical exponent of 1.
Oh, okay.
But
So,
that's what I got numerically, and I don't know if I have that plot with me. Let me just try to find it. Let's see. Yeah, I think that this is kind of the plot that you would be interested in. So this is a logarithm plot of the correlation length, and then this is the logarithm of the distance from the phase transition. And yeah, the slope is like -2/3, something like this.
okay, okay. Thank you.
Yeah, not a problem.
Arnab, these plots look much cleaner now than they used to.
Does it?
Yeah, there's no, did they used to have these little humps, so we didn't know what to make of them?
Yeah, I think there are two ways of extracting the data. One is like with the initial point included, and there was one, I think this one doesn't include the initial point, and then you have a more cleaner plot, but the exponent doesn't match, I think.
Yeah, so you say the two ways of extracting the data lead to different exponents?
Yes, I think one of them give you an exponent of 1, but the plots are not so nice. This one is cleaner, but gives you a different exponent. So I don't know what to make of it.
Okay, I think we need to, maybe we can ask Alberto. Yeah.
Yes,
So
certainly.
there's still some uncertainty about the critical exponent.
Yeah, maybe we should have a discussion about that.
So maybe, yeah, using the plane distance, right? Or this, there is a chord function because this is a finite system.
Yeah, I mean, increasing these different plots are for different values of the system size. And I think, shouldn't I approach the thermodynamic limit when I'm like 500 or something like that?
Yeah, definitely. But what I'm trying to ask is, this plot is log of the correlation. Can you explain again what this plot is?
Yeah, this is the log of the correlation length, and this is basically the distance from the phase transition. So the phase transition happens with this weird notation. It happens at pi/4. So this is basically the distance from the phase transition. So does that make sense?
Maybe it depends on how you estimate the correlation length on the y-axis. Right?
Say that again.
So we can discuss this offline, but I think it might depend on how we estimated the correlation length.
Yeah, exactly. Yeah. How we estimate the correlation length. I extracted it from how the string order parameter decays. And that kind of gives me a length scale.
I see. Yeah, it looks a little bit weird. Doesn't look like so linear. But
yeah.
If I can just, well, as I'm already talking, Alberto, you see the black dashed curve, the lowest curve. So it bends off, and that is the finite size effect. You see, it's the smallest curve. So when you get close to the phase transition, you feel the finiteness of the chain, the earliest. And all these curves bend off, but the longer the chains are, the later it happens.
Sorry, Robert, I cannot hear you very well. Can you repeat this last sentence?
Okay, sorry, maybe it's not an important comment. I just wanted to explain that in this plot, you see the finite size effects. So the lowest curve that ends at 0.5 is for the shortest chain. Yeah, and you see when you get very close to the phase transition, when the length scales become very long, it feels the size of the system. So the lowest, so the n equals 51 curve bends off the earliest. And the n equals 101 curve bends off second, and so on and so forth. So I just wanted to illustrate that you see the finite size effects in this plot. All I'm saying is probably obvious to you. I just wanted to point it out.
Yes. I wonder why you used an odd number of qubits, but just for fun, or why 51 under 1?
So it's just a MBQC thing. The analysis becomes easier if you are dealing with the odd chain. But
I see.
That's just, yeah. I mean, I already had the standard techniques. I mean, I can always just do it for even chains, but just being lazy, I guess.
Because you might have an extra Kramer's degeneracy, maybe, associated with an odd number of spins. But maybe, I don't know. Like my kind of, but I don't think this is going to affect the results. But yeah, yeah, I see the finite size effect, but it's a little bit. Yeah, maybe we can discuss it offline. Yeah.
Sounds good. Other questions?
Yeah, Arnab, I'm like sorry for this question, but I didn't quite get like where from did you get that you can use the point with the least separation?
We get it from this curve here, no?
Yeah, so I mean, is it like numerical evidence, or I thought that was
you can actually analyze this function here and use an exponential fit for the string order parameters and show analytically that this is a strictly increasing function of delta, and that is what you want. The numerics just confirm it, I mean, but analytically you can show that this function is a strictly increasing function of delta.
So that's the only thing that matters.
Yeah, I mean, this is just a picture that shows that effect. But.
Okay. Yeah, then if I also wanted to say that there should be a discussion session about SPT stuff. And I think we can plan it for tomorrow morning, if I understand correctly.
Sounds good.
Diagram preservation.
Yeah, so that's a question. Like, I didn't understand. The diagram preservation thing is for everybody, or is it a closed discussion for?
Well, we originally thought it would be closed discussion, but I mean, it's open to anybody who's interested.
Okay.
So we were afraid having too many people in the discussion, but that's not going to be the case. So, yeah, so whoever is interested in having that discussion, please call Michael, and Michael will send you the link.
Okay. Well, when are you having it?
It's at 9. I don't know how long it's going to take. Maybe it takes half an hour, maybe it takes 3 hours. Open-ended, we don't know. But tentatively, you could maybe schedule an SPT discussion for 11.
Yeah, maybe 11. 11 or 10:30. I mean, yeah, I think 11 should work. We could go to the lunch break. Yes. So because I think for Arnab, it's important that it stays as early as possible.
Yes.
So
Well, I mean, there's really enough SPT people. I don't really need to be there. You can also schedule it for earlier, or schedule it for 10, and then maybe join later if you can.
yeah,
You
so
know, it's up to you. Schedule it how you see fit.
yeah, okay. Then probably I will distribute a small doodle right now. So tomorrow works for everybody, right? Yes, tomorrow morning seems good, and I will ask what time people think is the best. Yeah, thanks.
Thank you. Okay, I'll stop sharing. Is there are no more questions?
Okay, then thanks Arnab again.